Okay, so here's some problems. We're working our way up the complexity ladder. So these again are cantilever beams. We now have a uniform load and a triangular distributed load. I am going to shortcut them again a little bit and just quickly compute that the shear force at the cantilever is going to be equal to W naught L, and that the moment will be equal to W naught L squared over 2. If I gave you a minute, you could easily figure those out. And you can see the shear force is what? Positive or negative? Positive. And the bending moment is? Negative. So we know where we're going to start. When we hit this free end, what's going to be the shear force? Should be 0. Now there's no applied force there. This is a distributed load. And what will the moment be? 0. It's free, right? So what do we do? Well, we're going to apply our relationship. So we know that the change in shear is the area under the load diagram. So let's do that first. So I know that I'm going to start with a shear value of what? Positive W naught L. So what's the change in the shear? Well, I look at my load, and the load is continuous, so that's going to be pretty easy to calculate the total area under that curve. What is the total area under that curve? It's a rectangle, base times height. So it's W naught L. Is that positive or negative load? Negative. So if I start at positive W naught over L, and the change in shear is negative W naught over L, what should be the value here?
Negative W naught over L.
0. Positive W naught over L, and the area is negative W naught over L. You add them together, you get nothing, right? So what should the shape of the curve there be? Well, our relationship says that the slope of the shear diagram is equal to the load. Starting right here, what would be the slope right there on my shear diagram? Right there. What would be the slope? If I had to measure the slope at that point, what would it be?
0.
Well, the slope of the shear diagram is equal to the value of the load. What's the value of the load? Negative W naught. And does it change? No, so it's constant slope. What kind of line has a constant slope? Mr. Rippey?
Horizontal. I meant...
The other one you always say.
no, don't say that.
Well, it's because that one, you can only say that when this is the time to say it.
A straight line?
Straight line. What kind of slope? Negative slope. So if I were to measure that slope, it would be negative W naught to 1. So I have a linear distribution of the shear across the beam. Where's the maximum shear? At the fixed connection. All right, let's do the moment diagram. What's the moment where we start? According to this, it's W naught L squared over 2. Is that positive or negative bending moment?
Negative.
Negative. What do you think the moment's going to be out here on the free end?
0.
0. So let's see if we can make those two things match up. We know that the change in moment is equal to the area under the shear diagram. Can you calculate the area under the shear diagram?
Yes.
Yeah, it's a rectangle. 1/2 base, which is L, times height, which is W naught L. That's a positive area, and that should be W naught L squared over 2. So if I start at negative W naught L squared over 2 and add W naught L squared over 2, I get 0. Isn't that cool? I also know that the slope of the moment diagram at every point is equal to the shear at every point. What is the value of the slope of the moment diagram right here? You would just slide up and read the value of the shear, which is what? W naught L. And is that positive or negative? Positive. So I'll draw it as a positive value. And I'll even squeeze in the fact that it is W naught L to 1. Is that going to stay constant? No, point by point it decreases, and it decreases all the way to 0. What's 0 slope, Mr. Rippey?
Horizontal line.
Correct. What kind of quadratic curve can fit those two things? One that starts with a slope and decreases to 0. So there's the distribution of my maximum moment. Do I really care what the moment is right here, where I kind of guess the curve? No, I just care where my maximum value is. And what is it? Minus W naught L squared over 2. If I was really concerned, like, I got to know what the moment is right there at 0.35 L, then you need to write an equation. Usually, we don't care. We just care about the max.
Now, for example, are we going to care or not?
You always care at the exam. Well, you should, whether you choose to or not. Again, it's optional. All right, so constant, first order curve, second order curve. Now let's just examine this one. What kind of order curve is this? This is first order. So you'd expect what here?
Second order.
Second order,
Third order.
third order. So let's see what we get. Again, I'm going to kind of short circuit this a little bit and quickly calculate that the shear value there is going to be W naught L over 2, and that the bending moment will be W naught L squared over 3. Again, if I gave you some time, you could figure that out. But that's not the focus right now. So what kind of shear is that? Positive. What kind of bending moment is that? Negative. We've done that a few times. So let's start our shear diagram. So our shear diagram is going to start off at a positive value of W naught L over 2. It's probably going to be what here at the free end? 0. So the change in shear from 0 to L should be the area in the load diagram from 0 to L. What's the area in the load diagram? It's a triangle. 1/2 base times height. So 1/2 L W naught. And that's positive or negative area? Negative, because the load is negative. So if you start at positive W naught L over 2 and subtract W naught L over 2, you get 0. What's the slope of the shear diagram? It's equal to the load. So starting right here, what's the slope of the curve right there? It should be equal to the value of the load, which is 0. What kind of slope is 0, Mr. Rippey? Excellent. And that slope is going to increase to a maximum value of W naught. And is it positive or negative? Negative slope is like that. Negative W naught to 1. So find a quadratic curve that fits that. What's the maximum shear in the beam? W naught L over 2, and where does it occur? At the cantilever. What kind of shape is that? It's a half of a parabola, exactly. If you look in the back of your book, there's a formula for the area of half a parabola. It's 2/3 base times height. So I can easily calculate the area of that. Why would I care to calculate the area under this curve? Because it tells me the change in moment. And what is the beginning value for our moment? W naught L squared over 3, positive or negative? Negative. So the change in moments, the area of this curve, and the area of that curve, because it's a parabola, is 2/3 base, which is L, times height, which is W naught L over 2, which is positive area, which is W naught L squared over 3. So you start at negative that, add it to it, you get 0. And we should get 0 for the moment here, right? What's the shape of the curve? The slope of the moment diagram is equal to the value of the shear. What kind of shear is that? Positive.
Positive shear.
And it's kind of large. And it decreases to... So this is going to have a 0 slope. And over here we're going to have a positive slope. In fact, if I tracked it, it would be W naught L over 2. And I just kind of find a curve that fits that. And there's the shape of my moment. First order curve, second order curve, cubic curve. Again, if you're interested in the value at some intermediate distance here, you're going to have to do a method of sections or do some other technique to actually write the equation that's continuous. Any questions about that? No?